Okay, hello class. Next topic in chapter 1 is lines, and we had a little bit of preview at the end of the last video, and we're ready to jump into this. So just to point you where you are in your journals, there's a page titled Lines, and we have this box in the middle that has some important facts for us. We're going to talk about lines that go through the origin, lines that are through another point, and line segments. So again, we have all the machinery there. It kind of makes sense. If you have a point and a vector, you're almost got a line. So I'm going to start with lines to the origin. Easiest type to define, but this is the first time we've seen a parametric function. So we'll start with R3 lines, but again, we can generalize this to Rn, which is really cool because it gets into my graduate classes in optimization. We're going to think in like 1,000-dimensional space, but we're still using the same equation for a line. It's just going up to 1,000-dimensional vector. Okay, so this is what I call a parametric function. It has one parameter in this case, the parameter t. It has this parameter t as input, one parameter. Later we're going to get to two parameters, and instead of creating lines, we'll create surfaces. But for now, we'll start simple, and we're going to create lines by having one parameter, but what it outputs is a vector. And that vector, also you can think of that vector as just tracing points through time. So again, as the parameter extends through its domain, this vector is just getting stretched, shrunk, or turned in the opposite direction, right? So maybe let's jump to an example. Suppose I wanted to graph RT equals T, 2T, 3T, start real simple, right? Well, that's our parametric function. Given an input T, it'll spit out a vector, which is also can be thought of as a point that's moving through time. And this vector is really just also another way of looking at it. It's just the vector 1, 2, 3. So some vector in three-dimensional space, let's say that's the vector 1, 2, 3 right there. And then it's multiplying by a scalar t, which we know extends it when t is bigger than 1. For t with between 0 and 1 fractional values, it shrinks it. And then for t negative, it can shrink it until the negative values get bigger than 1, and it'll extend it in this direction. Which then would sweep out for t between, they always have to give you a domain that you're interested in. If t is between minus infinity and infinity, this creates a line, an infinite line, right? But I could also have said, say, t between 0 and infinity, including 0. This creates an infinite ray. These are the ones we use a lot in my graduate classes, these rays pointing in one direction. We're not so much interested in the back with the negative. What if you said t was between 0 and 2, let's say? That creates a line segment. So in that case, it would take, if this was the vector v, 1, 2, 3, and it already is its given length, if you multiply by 2, it would just get twice as long. So we just have 2 of these. There you go again. Right, so that would be the line segment. T is 0 here, t is 2 at this terminal point, t is 1 here, t is a half, right? So if you take a look at t, what's really neat is if you plot t through its domain, it's giving you a direction, an orientation of the curve. I could define this same curve, but say go in this direction, and the orientation will be going this way. And you'll see some examples in your activities in the beginning there of how you can manipulate t and its domain to make the direction of travel either forward or backward along the line. And same thing for a space curve. Things that get curvy, when we get to chapter 2, I can define the travel along the roller coaster in this direction, or if it's the Rebel Yell at King's Dominion, used to be able to ride that in the backwards direction as well. So I can define that just by playing with how I define the domain t and maybe just substituting negative t in there and then changing the domain. That's often a trick that works to change the orientation. Okay, so that's our easiest type of line segment that would go through the origin. We could draw that on, we know it lives in R3, but we could draw it in R2. I think this one's not too bad to draw. The vector v is 1 along the x, 2 along the y, and then 3 above there. So this would be the vector v equals 1, 2, 3. And then if I'm doing the line segment, it would just be doubling that. That would be using this part here. Let's say from there to there. If I'm doing the entire infinite line, it would go like that. That would be r of t equals t, 2t, 3t from negative infinity to infinity. Okay, let's see what else. Those are lines through the origin, and again, we can extend them to Rn lines in general, just by going v out to n. But what if we wanted to go a line through a different point besides the origin? And we'll often call this point like R0, and it usually have components R1, R2, R3. Oftentimes you'll see we comfortably move back and forth between the brackets and the parentheses and points and vectors because they are kind of the same thing, right? We often think about a vector as being defined by its terminal point, and that point also, if you started at the origin, would create a vector. So we'll move back and forth between those. So if I had some point R1, R2, R3, and I'm going to have a vector that I'm moving in, this just gets extended to R0 plus TV is the shorthand, but remember that R and V are vectors. Think of them as boldface. So it's R1, R2, R3 plus T times V1, V2, V3. That's lots of letters and symbols, so let's just make an example and make it concrete. So the line through the point, let's say 0, 2, 1. In the direction v equals, let's try 1, 0, 4. Find the line through this point. So we'll make it a specific example. Now it's just applying these new definitions, but we can visualize what's happening too. We can just think there's some point in space, there's some vector, and this point is no longer at the origin, it's just moved here. So that vector just gets shifted up, and now we're doing the same thing. We're taking this parameter, parameterizing it, and making it move through that point in either infinitely in one direction or both, or for a line segment. Okay, so our equation of this line would be R of t equals 0 to 1 plus t times 1, 0, 4, which is t 2 plus just 2 and 1 plus 4t, right? This is the parametric function, and also just to note some more vocabulary, we often call the first component like your x of t component, your y of t component is your second, and your z of t. Because remember, these are also points in space x, y, z's, and they may involve t. So it's just saying that where you are in the x direction versus the y direction versus the z depends on the time of travel. Okay, so that's the parameter. That's why it's been parameterized. And so we can plot this, and then we'll use Tectile also to show you how to do it. But you can plot these for R3 ones. They're pretty simple. So let's start with our vector, 1x, 0 along the y, and 4. So it'd be something like this. This is the vector v from the origin. But we want that vector to be shifted up to the point 0, 2, 1. So that's 0, 2, 1. So this extends in both directions, creates the line R of t equals t to 1 plus 4t. You can write it that way, or if you like this notation here, which makes it very clear the point and the vector. Often this is helpful when you're inputting into a text tool. Yeah, so we have points through the origin, lines through the origin, lines through another point, line segments, and that's all controlled by the domain that they give you. If they don't give you a domain, you assume it's minus infinity to infinity. But let's do an example then, and then we'll get to a tech tool that visualizes these. So let's look at these lines. All right, so this is just a good way to test several concepts with this question. I have two lines. Hopefully, again, you're going to be pretty quick at recognizing those just by looking at a parametric equation to be able to tell whether it's linear or nonlinear. Same things that held back in R2 and R3 work. So this R of t is linear because it's linear in its variable. The only variable is t is the parameter. It's definitely linear. Each component looks like a linear function, right? Same thing for s. I could have used t here, but we'll see why that would be confusing to answer this. So let's just set it as a different parameter for now. And these are didn't give domains for these, so we're assuming t goes from minus infinity to infinity, s goes from minus infinity to infinity. So there's two infinite lines shooting somehow through R3, and we're wondering, do they touch, do they intersect, and could we find that point of intersection? Okay, so let's just visualize this. And again, you could plot these. An easy way to visualize them would be to separate them out into their points and their vectors. So this would be the point 3, -2, 1, plus parameter t times the vector 2, 5, -1. Right, and so then you can visualize that and graph it just like we did with the last example. And the same thing for this next one. S would be at the point 7, 8, -1, parameterized in the direction of the vector -2, 1, 2. Okay, and you could try to do that in R3, but let's jump to a tech tool too, just to show you what can be done. Okay, so last time we talked about putting points and connecting with a vector. Let's just go straight to something new, which is a space curve. So I'm going to turn off those points and vectors and show you how to enter a space curve. So we have the most simple type of space curve. R of t is linear now, but we're ultimately going to get to R of t's that are nonlinear and very interesting. And so I enter R of t, and here's a crazy looking nonlinear one if you want to look at it. Really cool coil. And you can see that it's got this oscillating thing, and the trig functions might be a hint towards that, but we are not doing that. We're doing something much simpler, so we're just going to delete those and enter our space curves, which are linear space curves. And so we are going to take 2t plus 3 and 5t minus 2 and minus t plus 1. And we can say -2 to 2 just to look at a section of it, a line segment. You can also, if you touch this, change the color, which is helpful when we add more. And I can say I want to use a constant color to make it all red. And let's see, I can trace it. I can watch what happens. And it's tracing when t goes from -2. I can animate it, and it'll be tracing the points along that path. That's what the blue vector is actually showing, that R of t is actually a vector at any time or a point at any time, and it's tracing it. Sometimes that makes a little clutter on the graph, so I'll get rid of that. And then the orientation arrows, this is pretty neat too. It can show, maybe I want to put 3 arrows on there. And I can zoom out a bit. Actually, let me shrink this from t to 1. Zoom back in. What those orientation arrows are just showing the direction of travel. As t goes along its domain, I just showed a line segment here from -2 to 1. It's going in this direction. Again, there's ways to orient it if you really need to go in the other direction and you're doing some sort of physical application, which you will with your challenge problems. Okay, that is the first line, or a section of that first line. let me put in the second one. So I do that as another space curve. I already have one entered, so I'll enter it, change this one. And even though I have S's on the board, this program asks for all the parameters to be t, so no problem. I'll just call this minus 2t plus 7 and t plus 8 and 2t minus 1. And the question was, do these things intersect? And I haven't answered that. I've just sort of put them in their format, and we'll see if the tech tool is going to help us with that. Maybe I'll try putting this one in bluish color, maybe from -1 to 2 or -2 to 2. I might have to zoom out so we can get a better view. So you can zoom out up here in the bar or by, so let me change the range on the red one, the first one, and maybe say from -5 to 5. Now I'm in the zoomed out view. Okay, so I've extended, I've let the orientation be the same. Oh, and I forgot to change the color on this one. I thought I did that color, but I need to make it constant color. Okay, so we got a red line and a blue line. And I don't know, do they intersect? Well, you're gonna have to change your view, rotate it around. Maybe they intersect. Sometimes it's hard to tell. It looks like they do intersect. Well, how are we gonna find that point of intersection? So this is also another point that this tech tool helps you see, is that in R3 and higher, well, let's go back to R2. In R2, lines they're either parallel or they intersect, right? No other option. But in R3, you can be parallel, you can intersect, or you can be skew, which means non-parallel, non-intersecting. And hopefully you can imagine that in your room, in your desktop coordinate system, right? Just imagine some line through here and then another one. They don't intersect, but they're not parallel. You can see how the vectors are. How would you tell if two lines in R3 are parallel? What do you think? It's right here from your vectors. That'll tell you whether if the vectors are parallel, the lines have to be parallel. And then, of course, if they're parallel, they're not intersecting. But there is another type of non-intersecting, which could be skew. All sorts of ways of being skew. So really, this is another way of saying, are these lines parallel, intersecting, or skew? It looks like they're intersecting from the tech tool, but let's go ahead and show that mathematically. Oh, so yeah, follow up. So lines are parallel if these two vectors are parallel, which means they're scalar multiples of another. They're either identical or they're like one is 2 times the other, half times the other, whatever. So scalar multiples makes, if their vectors v are scalar multiples, they are parallel lines. Okay, but again, our guess is that they intersect. How are we going to find this point of intersection? Well, let's just think, what does it mean to be a point of intersection in R3 or Rn? In this case, we're in R3. Do these R3 lines intersect? Well, if they do, it means that they touch, which would mean their x components would have to match, their y components would have to match, and their z components would have to match. So let's start with that. 2t plus 3 minus 2s plus 7. Those would have to be equal. That would be our x component. The next one, 5t minus 2 would have to equal s plus 8. Last one, minus t plus 1 would have to equal 2s minus 1. All right, well, what do we have here? This is a system of equations. 3 equations, 2 unknowns, and actually it's a linear system, right? Linear in all the variables. It's a line, right? It would make a linear system. So if you've had linear algebra or are currently taking it, you might be doing something like this, where you have 2t plus 2s equals, is that 4? 5t minus s equals 10, and minus t minus 2s equals minus 2. Okay, so then this is a little easier, again, if you're taking a linear algebra class, or you might work with systems of linear equations. Even in high school, you've probably seen some of these. You could graph all 3 of these, because there's 2 equations and 3 unknowns. Sorry, 3 equations, 2 unknowns. You could graph those 2 unknowns. These really represent lines in ST space, or y-axis, however you want to look at it, and graph them and see if they have a point of intersection. So visually you could do it. If you're in linear algebra, you learn how to make something like this. 2, 2, 5, minus 1, minus 1, minus 2. 4, 10, minus 2. You did this system and you did Gaussian elimination, row reduction, echelon form, and tried to see if this thing had a solution, and it would spit out what it was. There's tech tools that do this as well. Or probably you remember also that to solve this, you could start by like working with the first equation. Let's make some space. And let's take this first one and solve it for one of the variables. Let's say we solve it for s. So s is going to be what? 4 minus 2t divided by 2. So 2 minus t. Is that right? Yeah. Okay, so this is a representation of s in terms of t. I could take that from equation 1, plug it into equation 2. So that would take this and put it right here for s. So I would get this like 2' equation. That would be 5t minus 2 plus t equals 10. So 6 t's equal 12. T is 2. So how would I solve for s? It's written right here. S in terms of t. If you give me a t, I'll spit out an s. In this case, the s would be 0. So I have a solution, but does that solve the third one? It was by design a solution that would solve the first two. And you could check that. If t is 2 and s is 0, 2 times 2 plus 0 is 4, check. If t is 2, that's 10 minus 0 is 10, check. Now we really hope it solves the next one. If it doesn't, then it's has no solution. The system has no solution. The matrix is not full rank, and you could go on with the linear algebra ways of now analyzing it. So does this work? Minus 2 minus 0 is minus 2. Yeah. Okay, so this solves the system, which means when t is 2 and s is 0. So in terms of its domain, you're riding along the first line and you get to 2 for your t value. On the second one, you start at 0, and that's your point of intersection. These two intersect. How do you figure out the point of intersection, though, given that? Well, remember, when t is 2, I'm plugging in to r of 2. And that just tells me when t is 2, it gives me this output of, let's see, 4, 7, 10, 8, minus 2, minus 1. And when the second equation is at 0, it gives me 7, 8, minus 1. And those are the same 2 points. Remember, these are vector functions. They output vectors, but vectors actually can be thought of as points by their terminal point. And so at time 0 on the second one, time 2 on the first one, they would intersect, which that's kind of neat too, to think about the applications of lines. Even though lines are so simple, you'll see a really neat application, and I think it's challenge 1, could be challenge 2. At the end of chapter 1, there's a challenge problem about planes that are flying in their paths, and they have different parameterizations, and they're just, typically in a flight, you're trying to get from point A to B, point B in the shortest distance, so that's a line. And so we have these flight paths, and the question is, do they intersect, and at what time? Even if they did intersect, but you're traveling at these points along these lines at different times. Like, okay, who cares if I intersect if I'm well beyond there, right? And then this one can come right through. So you get to do applications of lines, and we're going to use those repeatedly. Now, if you had to take a guess, why do you think lines are so important for us for space curves? Because not so much that, again, there are some applications, and you're going to work on them, but think back to why lines are so important in Calc 1. Even though we're talking about nonlinear functions, you stopped often and stopped and took a tangent. And that tangent line had a ton of information that we use all sorts of ways. Same thing's going to happen for space curves. Space curves. Through R3 space, we're going to stop and we're going to get a tangent line and a tangent vector, and it's going to have so many meanings and applications for us. All coming in chapter 2, but we got to get our basics. So done with lines. What's the next thing? That is a simple nonlinear or linear object in R3. It's just planes. And we've already learned quite a bit about planes from thinking of them as multivariable functions, but we'll extend that now to think of them as parametric functions. But rather than just one parameter, we'll have two. It's coming next.